This is section 8.5, partial fractions. This is another technique of integration, partial fractions, which we're going to talk about. What I would like to do is have you start with this idea. Let's say we had, for example, 2 over x plus 3 plus 5 over x minus 2. Of course, you know how to do that addition. At this stage in your journey, you know that you need a common denominator. And the common denominator for relatively prime factors of these two denominators, kind of like if I were asking you to add 2/7 and 5/7. Oh, sorry, didn't mean to make that 7 also. Let's make it 5/3. Then, since 7 and 3 are relatively prime, we need a common denominator, so we multiply this first fraction by 3 over 3 and the second fraction by 7 over 7 to get the same denominator. So we're going to do something similar here, of course. We're going to multiply this first fraction by x minus 2 over x minus 2. Guess I didn't need those parentheses. And the second one by x plus 3 over x plus 3, which produces 2x minus 4 when you distribute over our common denominator, plus 5x plus 15 over x minus 2 times x plus 3, our common denominator. And now that the denominators are the same, we add the numerators. So 2x plus 5x is 7x. Negative 4 plus 15 is 11. And if that factored, we'd want to factor it and see if anything would cancel. Since 7x plus 11 is prime, that's not needed, and so this would be our final answer. The question is, if you started with this, do you know how to get back to there? I know in college algebra you worked on adding fractions with variables involved like this. This process is called, if you take 7x plus 11 over x minus 2 times x plus 3, and we say that we resolve it into partial fractions. And that's the process by which we'll go backwards in doing a problem from something that looks like this and making it so that it looks like that up there. Okay, so let's go about this in kind of an organized fashion. I'm actually going to start with this one that we had because we know what the answer is supposed to be, and that will kind of inform us about the technique of resolving into partial fractions, to sort of think through the process we just did somewhat in a backwards fashion. So if you notice, the form of the answer is going to be some number, I'm going to call that number capital A, over one of the factors, x minus 2 for example, plus some number, let's call that second number B, over x plus 3. Now, the technique you learned in algebra about what you can do if you have a problem, or an equation I should say, that involves fractions just what do you do to solve that kind of equation? And the answer is that you want to multiply both sides of that equation by the LCD of all the fractions in that equation. So the two denominators we have are 2 and 3. They're relatively prime, so the common denominator is 6. So I'm going to multiply both sides of the equation by 6. And the result of that is that when you distribute, 6 times 2/3 is 4x, plus 6 times 4 is 24, and 6 times 5/2 is 15. You now have an equation that doesn't have fractions in it. So that's what we're going to do down here. We're going to multiply both sides by the common denominator, which will be x minus 2 times x plus 3. Okay, so on the left side, if we multiply that fraction by both of those factors, they will cancel the denominator, leaving 7x plus 11. Multiplying that product x minus 2 and x plus 3 by the first fraction, because we're distributing, the x minus 2's cancel, leaving the a to be multiplied by x plus 3. And in this, the last example, the b over x plus 3 being multiplied by x minus 2 and x plus 3, the x plus 3's cancel, leaving b times x minus 2. Then what I'm going to do is I'm going to make up a number that I think would be helpful. I'm going to let x equal, I'll just make up something. How about -3? That sounds like a great number. And x equal -3 and substitute into both sides of this equation. So 7 times -3 is -21, plus 11 is -10. -3 plus 3 is 0. A times 0 is 0, so the a is gone. Then -3 minus 2 is -5, so that's going to be -5 times b. And that gives us an equation which we can solve for b. Using division, we get b equals 2. Then I might think of another number to let x equal. I was thinking of 2. I thought that would be a good number. Good enough, I guess. So let's go. 7 times 2 is 14. 14 plus 11 is 25 on the left. 2 plus 3 is 5 times a. And 2 minus 2 is 0. 0 times b is 0. So that leaves an equation which, lo and behold, we can solve for a using division. And so what that means is that 7x plus 11 over x minus 2 times x plus 3 resolves into these partial fractions, a, which is 5, over x minus 2, plus b, which is 2, over x plus 3. And let's check that out. Does that match what we started with at the outset? I intentionally covered it up so I wouldn't look and cheat. Yep, they're in reverse order, but that doesn't matter because we're adding, no big deal. Those are exactly the two fractions that added together to give us that. So that's the process we're going to do. Okay, so let's do another example here. Let me see, what problem do I want to do? Let's do this one. 1 over x squared minus 5x plus 6. Well, if you notice in the other one, we already had the denominator in factored form, so that's actually the first step that we'll need to worry about is factoring. So what factors of positive 6 add up to be -5? Of course, that's -2 and -3. And that will be equal to some number a over one of those factors plus some number b over the other factor. Then I'm going to multiply both sides of the equation by both x minus 2 and x minus 3. Again, that's on both sides of the equation. So when I multiply on the left side by those two, the x minus 2 and x minus 3 cancel, leaving the 1. And multiplying both of those by this fraction with a over x minus 2, the x minus 2's cancel, leaving a times x minus 3. Then, same idea, x minus 3's cancel, leaving b to be multiplied by x minus 2. Now last time I just kind of made up some numbers out of thin air, you may have thought, but if you think about it, those were fortuitous numbers to try because they made something equal 0, which made that letter A or B disappear. So what number would be a good number to use here? There are two good possibilities, and it doesn't matter which one you start with. I'm going to start with 3, because I usually go from left to right when I'm doing this. So now there's nothing to substitute into on the left side. We're going to get 1 no matter what on the left side. So 3 minus 3 is 0, a times 0 is 0, so that term is gone. 3 minus 2 is 1, 1 times b is b, which implies that b is positive 1. Okay, then the other number I might let x take on is the value of x equals 2. The left side will be 1. 2 minus 3 is negative 1, times a is opposite of a, plus 0, so a is negative 1. So therefore, this becomes negative 1 over x minus 2 plus 1 over x minus 3. All right, so why are we talking about this? It's maybe something you've talked about before. It's one of those advanced topics in college algebra that you may have actually done, but why? Why are we doing this in a calculus class? Well, the reason is, if I asked you to integrate this problem, you might think of u substitution, where u is the denominator. Unfortunately, we would need a 2x minus 5 in the numerator to act as its part of its du, which we won't have in this problem. And so that's not going to help us. But if we change this using the method of partial fractions into negative 1 over x minus 2 plus 1 over x minus 3 dx, then we should know how to do that antiderivative. So I'm going to do the first one kind of full bore, everything you might want to think about. So let u equal the denominator. Du in this case is 1 times dx, which we will have. And so we pull that negative 1 out, and we'll have negative 1 over u du. And if we did the same thing in the other one, we would get, let's call this one v dv. And when it's that simple, like v is equal to x minus 3, its derivative is 1 dx, and the derivative of v would be dv, just like I wrote there with the u. I'm not going to require that you go over here to the side and write that when it's that simple. That one you can do by inspection. And then the antiderivatives are negative natural log of the absolute value of u, which is x minus 2. Notice I skipped a step. I didn't write natural log of u in reality. I just went ahead and substituted. And this will be natural log of the absolute value of v, which I know I didn't write it down, but I was thinking of it as the x minus 3, plus c. And there we have an antiderivative answer. No muss, no fuss, no bother. Now, as far as alternate forms, you might want to remember that the difference of two logs, let me rewrite this in that order. The difference of two logs is a single logarithm, and the answer may show up like that as a single logarithm. This would be the natural logarithm of the absolute value of the first thing divided by the second thing. So your answer might end up looking like that. So something to pay attention to. The form of the answer might not be exactly what you think it would have to be. I would actually take that third from the bottom line as a final answer, but you might see like a multiple choice question, they may very well go to here. So you need to be aware that that's a possibility. Okay. So, so that's a good way to do this. And so let's do another example. Or let me first talk about what types of things we might encounter, because the ones I've given you are pretty tame and pretty easy. So let me show you some that are maybe not so tame. If, for example, you had 2x plus 1 over x plus 3 times x minus 4 cubed, where notice you have a repeated factor. With that power on x minus 4, it's repeated. It's in there multiple times. And what happens with those, of course, the easy thing, x plus 3, that's going to get an a over x plus 3. But for repeated factors, you don't know. It could be that you had several fractions who would contribute to that being a part of the common denominator, but we don't know. So what you have to do is you have to use every power of that repeated factor from what it's given as, so x minus 4 cubed, all the way down to it to the first. So every single power has to be accounted for between x minus 4 cubed and x minus 4 to the first. We need a fraction for every single one of those possibilities. Now, it may happen to be in this problem that it would have maybe b is equal to 0 or c is or d is equal to 0, and you really didn't need all of those. But you have to allow for that possibility. Okay. And we could go back and do that one later, perhaps. I'm just trying to set up different things that can happen at this stage. So another thing that could happen is you could have a regular old x minus 4, I suppose. It's fine. Just making this up. But then that could be multiplied by a quadratic factor that doesn't, a quadratic term that does not factor. X squared plus 3 is prime. It doesn't factor. And so what we'll do in that case is the x minus 4, notice when it's linear, like x plus 3 or x minus 4 is linear cubed or squared or just itself. Those are all linear factors, and the exponent makes it a repeated factor. So notice that we always put just a letter like a or b or c over those linear factors. But what changes over here is if this is quadratic and prime, then we have to allow for every power up to 1 less than the denominator power. In other words, if this is quadratic power 2, I need to allow for a linear term and a constant. So the power of the denominator there is 2. 2 minus 1 is 1. So I have to allow for every power of x up to and including 1. Now for the first fraction, x to the first is to the first power. I have to allow up to x to the 0 power of x. And of course that's equal to 1, which means that just some constant will be there. If I had, for example, a cubic term, I would have to allow for up to 3 minus 1 is 2. I'd have to allow for a quadratic numerator in that case. So ax squared plus bx plus c. Now it could be that some of those things are 0. We just have to allow for every single one of those as a possibility. We don't want to shortchange ourselves on that. So those are a couple of things that are going to happen that are more challenging, and I bet that these two types of things were not covered in a college algebra class. Even if you did some partial fractions, that probably was not included. By the way, that problem we did a few minutes ago, the answers you can see right there above, we could have done that by completing the square and using trig substitution. And I'm looking at my notes, and that would have taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps. No, 11 steps to get to that same answer. We didn't take nearly that many. And the things we're doing up here are just simple algebraic steps. So that's something that you want to realize is the ease of this compared to the trig substitution is way, way easier that way. Okay, so let's go ahead and do these two while we're here. Can't hurt. So let's decompose the 2x plus 1 over x plus 3 times x minus 4 cubed. So I'm really just writing that same line again that I did above, because I didn't leave any room below it, which I probably should have, but that's okay. So this factor is a linear factor that has a power on it. Just because the power is 3 doesn't mean it's cubic on x. It's the factor's degree that matters, not how many times it's repeated. So I do not need for this a bx squared, etc., because the factor itself is linear. Okay, so this is over linear x minus 4, which happens to be squared, and d over x minus 4. Okay, so in these more advanced examples, my trick of thinking of a special number that's going to be really, really helpful is unfortunately not going to work as well as we would hope. All right, but we are going to start the same way. We're going to multiply both sides by the common denominator of all the fractions in the problem, which, by the way, is the same as the denominator on the left-hand side. So if I multiply the fraction on the left by both x plus 3 and x minus 4 cubed, the denominator cancels, leaving 2x plus 1. Multiplying both of those factors by the first fraction on the right, the x plus 3 cancels, leaving a times x minus 4 cubed. Multiplying both of those by the second fraction on the right, I'll cancel x minus 4 cubed, leaving b times x plus 3. And the next one, I'll multiply 2 of the x minus 4's will cancel, leaving the x plus 3 times a single x minus 4. And for the last one, a single x minus 4 will cancel, leaving d times x plus 3 times x minus 4 squared. Okay, I can see this is going to be really complicated. So maybe I'm getting in over my head a little bit early on this, but I think it's worth talking about because you may very well have a problem like this. So x minus 4 quantity cubed is x cubed minus 12x squared plus 48x minus 64. Someone needs to probably check that I did that correctly. Then here I'll distribute. Notice that this process right now is different because I'm actually not substituting for x, which might give us some information, but it won't give us everything. Okay, and this will be x squared minus x minus 12. And that multiplies to be, I'm not going to be able to do that in my head. So x squared minus 8x plus 16. Okay, so 2x plus 1 is equal to ax cubed minus 12a x squared. And I really am hoping that when I did this cubing in my head that I didn't make any mistakes. I may have, and so I may end up being really sad about a bunch of mistakes that are going to carry forward. But let's just assume that I haven't made any mistakes because the process won't change based on those mistakes. We'll just get wrong answers, but the process I'm going through won't change. Okay, so this will be x cubed, and I'm going to distribute the dx cubed. I'll have negative 8x squared plus 3x squared is negative 5x squared, so negative 5dx squared. I'll have 16x minus 24x is negative 8x, so minus 8dx. And 16 times 3 is 48 times d is 48d. Boy, I sure hope that that's all correct. I'll be really sad if it's not. But I wanted to show you one like this regardless. Now, the good thing about equations is, and this is kind of a very basic middle school, early high school idea, is that the two sides have to be the same. That's why the equal sign is valid. So everything on the left has to equal everything on the right. So if we carefully look at this, on the right side there are coefficients on x cubed terms, and I'm going to pick those up. So a, keep looking for x cubed terms, plus d, a plus d, those are all the x cubed terms. Those coefficients have to add up to be equal to the coefficient of all the x cubed on the other side of the equation. Since there are no x cubed, that must be 0. So there is 0x cubed on the left, which is equal to ax cubed plus dx cubed. So 0 is equal to a plus d. Okay. Now, next highest power, let's look for all of the x squared terms. So that's negative 12a, x squared, x squared, x squared, x squared, plus c, x squared minus 5d. That's all the x squared. has to equal the coefficient of x squared on the left side of the equation. Since there isn't one of those, its coefficient must be 0. Okay, now let's look for, see, x cubed, x squared, now x. So 48a x plus b. Notice as I underline that, make sure that I don't miss anything and that I make sure every single thing here is considered. Minus c minus 8d equals the coefficient of x on the left side of the equation, which is 2. And then finally, the constants, negative 64a is a constant, 3b is a constant, negative 12c is a constant, and 48d is a constant. And all the constants on the right side have to add up to equal the constant on the left side, which is 1. Now, what this has formed, of course, is what we call from algebra a system of equations. Our system of equations has 4 equations with 4 unknowns, a, b, c, and d. So to solve that, we could do a bunch of different things. In algebra, you learn a bunch of different techniques for solving systems of equations. One of my favorites, and I hope you saw this in an algebra setting, but it's called well, it's using matrices, I guess is what we may say. So I'm going to show you how to do this, and you will need your calculator, so you might as well pause and get your calculator out, your graphing calculator. But first, this is what we'll do. We're going to write a matrix that consists of all of the coefficients of a, b, c, and d for each of those equations. So for the first one, we have 1a, 0b, 0c, 1d. Okay, so you have to account for every letter, and they have to stay in that order. So the coefficient of a in the second one is negative 12, 0b, 5c, and I'm sorry, I was getting ahead of myself. That's 1c, excuse me very much, and negative 5d. Okay, the third one is 48a, 1b, negative 1c, negative 8d. And the last one, negative 64a, 3b, negative 12, c, and 48d. Now if I were to close off this matrix, this would be what you call the coefficient matrix of that system. The coefficients of a, b, c, and d in that order for each of the equations. Then I'm going to augment that matrix with the constants on the right side. So that's 0 for the first equation, 0 for the second equation, 2 for the third equation, and 1 for the fourth equation. That's what we call an augmented matrix. And it represents that system of equations above it. You may have learned this technique, and by hand it's kind of long, especially with 4 equations and 4 unknowns. I don't want to do it the long way. I want to show you the short way. What we're going to do is we're going to type that matrix into our calculators. So let's talk about how that works. From the home screen, you need to get the matrix menu. Matrix is right above on my calculator, the X to the negative first button. So when I say get to the matrix menu, you're going to hit second and then X to the negative first. You read across the top, names, math, edit. The first thing we're going to do is edit, so move to the right twice. and edit any matrix. I usually am lazy and just pick the first one and hit enter to edit matrix A. Now, what you'll see there is some number times another number, and that's not really multiplication, that's a size, kind of like a 2 by 4. A piece of wood that's 2 inches by 4 inches. These are the dimensions of the matrix, and it always is number of rows first. We have 1, 2, 3, 4 rows, so type a 4, enter. By the number of columns, we have 1, 2, 3, 4, 5 columns. And then input all of those entries. 1, enter, 0, enter. It reads like a book. 0, enter, 1, enter, 0, enter. And it goes back and you can do the second row. So I'm typing this in, negative 12, enter, 0, enter, 1, enter, negative 5, enter, 0. Okay, so I'm going to do the rest kind of without talking my way through it. Hopefully you are also doing this at the same time. Be very careful that you don't mistype. Okay, so I'm typing the fourth row now. Negative 12, 48, and 1. Okay, when you're done, you probably can't see the entire matrix, so I'll show you how you can kind of look at it. So if you hit second mode, which is quit, you'll be in your home screen. Go back to the matrix menu, and this time choose names A, the one we just did. Notice it now says next to that it's a 4 by 5 matrix, 4 rows by 5 columns. Hit enter, number 1, and it will paste matrix A into your home screen. Hit enter again, and you should see your matrix. And if you have some dots on each row, that means that part of it you can't see, so you're going to have to hit the right arrow to see the rest of it. But you should double check that all of your entries that you've typed in are correct and in the right places. Not accidentally a negative when it's supposed to be positive or vice versa. So check every single number. Okay, once you're convinced that that's good, then what you're going to do is you're going to find a command, and this is what you write on paper, by the way. You write the augmented matrix, and in front of it, you type the command that we're going to do to it in the calculator. And this tells me that this is what you're doing by writing RREF in front of that, and then parentheses around the matrix. You're going to do that command. So let's find that. So go to the matrix menu. This time go over to math and go way down and look for RREF. It's way, way, way down there. Choose that. Make sure it's RREF, not REF, but RREF. Then it's waiting for you to tell it which matrix you're going to perform that operation on. It has left parenthesis and then blinking cursor. So go back to your matrix menu and pick up name A again. It'll paste matrix A in behind it. Then as a precaution, I would like for you always to convert your answer to a fraction, just in case, because I don't want to see 0.1011010 or something like that. I want to see a fraction that's equivalent to that if there is such a thing. So before you hit enter, hit math. The very first option is convert to frac. So choose that and hit enter. And you should see, if I made up something that's actually doable and good, you should see 1, 0, 0, 0. And then they don't have that vertical bar in there. That's just the visual clue that that's the augmentation, the addition of the constants on the right side of that bar, and the coefficients of your variables on the left side. Okay, so I'm just copying down what I see, and on paper I would want you to do this as well. I want to see what you saw in your calculator. So I would want you to write down as a recording, this is your work for these problems, is to write this stuff down, including the RREF out in front now, all that good stuff. Okay, and the last row, had to move the cursor down a little bit to see the whole thing. Wow, what a messy problem. Well, since I made it up on the spur of the moment, I'm not surprised that the numbers are pretty nasty. But at any rate, if you take this back into a system of equations, that first row says 1a, which is a, plus 0b plus 0c plus 0d equals 5 over 343. The second row says 0a plus 1b plus 0c plus 0d equals 9/7. The third row says 0a plus 0b plus 1c plus 0d is equal to 5/49. And the last row is 0a plus 0b plus 0c plus 1d is equal to negative 5 over 343. Okay, and so what that implies is that, pull this down a little bit. If I remember, so I'll have this written down on my own piece of paper. Okay, a was over x plus 3. Oops. So from above, that's equal to 5 over 343 over x plus 3 let's see, what was the next one I wrote? B over x minus 4 cubed. Okay. Plus b 9/7 over x minus 4 cubed plus c, which is 5/49 over x minus 4 squared plus d, which is negative 5 over 343 over x minus 4. Okay, so that's how that works. Okay. I guess while we're doing it, we can do the other one that I set up earlier as well. I have that written down here someplace, so I don't have to scroll back. That was 3x plus 7 divided by x minus 4 multiplied by x squared plus 3 so that's going to be a over x minus 4. Linear denominator means constant numerator, and prime quadratic factor in the denominator means that we have to have a linear numerator, so bx plus c. So I'm going to multiply both sides of this by the common denominator, x minus 4 times x squared plus 3 the result on the left will be 3x plus 7 equals a times x squared plus 3 plus bx plus c, notice the parentheses around the binomial, multiplied by x minus 4. Okay, so doing the multiplication on the right side, I get ax squared plus 3a plus negative 4bx plus bx squared plus cx minus 4c. Okay, so the coefficients of x squared are a and b, so a plus b has to equal the number of x squared on the other side, which is 0x squared. Now the x terms is this one and that one. So negative 4b plus c will equal the number of x's on the other side, which is 3. And then finally, the constants 3a minus 4c should equal the constant on the other side, which is 7. So you could do the technique using an augmented matrix and your calculator if you wanted to. It's not always necessary. This one is not too bad to use another technique, and let's pretend like this is one where you couldn't use your calculator. Let's see if we can figure out how to do this, just in case. So what if I were to solve the first equation for b, and then substitute that answer into the next equation down for each b? I'm going to put the negative a in its place. This is called substitution. And that would simplify to be positive 4a plus c equals 3. So, and I didn't just kind of stumble into doing that. I was thinking ahead. I was trying to rewrite equations in terms of the same variables. So I combined those first two by substitution, and I'm going to keep the third one the same. And I can combine these two with a process called linear combinations to eliminate either the a or the c and solve for the other one. So what I'm going to do is I'm going to multiply the top equation on both sides by 4, which will give me 16a plus 4c equals 12, and leave the second equation alone, so 3a minus 4c equals 7. And then adding those two equations together, I get 19a plus 0 equals 19. This looks like one I contrived because I'm getting nice answers. Oh, well, either that or I lucked out, which means a is 1. And then what you do next is you do what's called back substitute into the next level into one of those two equations that have a and c in them. It doesn't matter which one. I'm going to use the first one. 4 times 1 is 4 plus c equals 3. I can solve for c by subtraction. Okay? Then we're going to go back another level to one of the equations in this level where there are, well, potentially 3 variables. This one had 2 in each one because there was a 0 something in each one of them. But knowing a is 1 and c is negative 1, we can choose any of those, and doing substitutions figure out the remaining letter b. I'm going to use the top equation. So 1 plus b is 0, which means b is negative 1. And so consequently, that original problem decomposes into 1 over x minus 4 plus the opposite of x minus 1 over x squared plus 3. And if you can't stand it that you have all those negatives in the in the second fraction, you can factor out the negative 1, which will leave x plus 1 over x squared plus 3. And that negative's in front, and the addition of a negative thing is subtraction. So you could write it in either of those two forms, and I really wouldn't care which one you chose to do, because they're both about the same. Okay, so now we've talked about decomposing into partial fractions. So we can now turn to well, let's talk just for a second about factoring, because I think this is going to be something that some of you may not be as good at as you should be, so you may need to review this. But for example, if you had a polynomial that had 4 or more terms, like this one, one of the things you're supposed to try to use when factoring 4 or more terms is grouping. So I'm going to group these 2 and 2. The first 2 separated from the last 2. Oh, that reminds me, how many of each kind of animal did Moses take on the ark with him? None. That was Noah. Moses didn't put animals on an ark. Okay, anyway, doing that grouping, notice because there was a subtraction, I changed it to addition, which meant everything behind that I'd have to use its sign. So negative x and negative 1. Then in each group, factor the common factor out. So x to the fourth, factor out, leaving x plus 1. In the second group, I'd factor out the negative 1, leaving x plus 1. And that's a good thing that we got the same binomial left from both parts. This is now a common factor. It's a binomial common factor. So I'm going to factor that out, just like I above factored out the x to the fourth. I'm now going to factor out the x plus 1. So I factor out the x plus 1 from the first group, x to the fourth is left. Minus, and if I factor x plus 1 out of the second group, the number 1 is left. Okay. Then x plus 1 is prime. X to the fourth minus 1 is a difference of 2 squares, which means it factors. It's the square root of the first term plus the square root of the second term times the conjugate of the binomial I just said. So x squared minus 1 is its conjugate. X squared plus 1 is prime. X squared minus 1 is not prime because it's a difference of 2 squares. It factors to be the square root of the first one plus the square root of the second thing times its conjugate. And those are all prime. There is a repeated factor. X plus 1 is in there twice, so I should have x plus 1 squared times x squared plus 1 times x minus 1. Just a little reminder about factoring down to prime polynomials. All right. So, now if you'll turn to the decomposition box there that talks about the decomposition of a n of x over d of x. And I mentioned this earlier, but if the degree of the numerator, and we're not going to actually finish this problem, I'm just using it as an example, is greater than or equal to the degree of the denominator, the first thing you're going to do is long division, polynomial long division. And the result will be that that's equal to something plus some remainder thing over your divisor, which in this case would be x squared minus 3. Okay. Then once you have fractions left, or it started out with, say, a numerator that's greater, the numerator power is less than the denominator power. Both of these cases are similar because that remainder over divisor will be of this type as well. This is where you'll use partial fractions, if you can, to continue. Okay. So use partial fraction decomposition for many of those problems to continue it. Okay. So then they talk about linear factors and quadratic factors, and how if you have linear factors, the numerator is going to be constant. If the denominator is a quadratic factor, the numerator will be a linear expression. And if you have repeated factors like that, one that we did before, the x minus 4 cubed, you have to represent every power of that repeated factor from the given one down to it to the first. And that's basically what's all in that box. So we talked about it. I just didn't quite use their example or their terminology exactly. So I think I'm going to move to another video because I've run out of room on this one. So go ahead and close this one and go to the next video.